So welcome everyone to the first Pacific Category Theory online seminar, the new seminar for those in the Pacific time zone. And I'm very happy to see that our first talk has lots of participants. So great to see you all. Our first speaker today will be Richard Garner, who's going to be telling us about enrichment. So take it away, Richard.
Thanks, JS, and thanks, Zainab, for taking the initiative to set this up with your um, co-conspirators. And it's an honor to inaugurate this seminar, and I hope it continues. Uh, well, hopefully the quality of the talks improves after this one. That's what I should say, right? But I hope it continues for a long time and gives us lots of fruitful interactions. So I'm going to talk about universal enrichments of categories. I can't remember if that was exactly my title, but uh, that will do. Of categories, and I was very bad. I forgot to say when I sent you the abstract. So this is something that I did with uh, a former PhD student of mine, Hyun Tai Young. So this was a project that we worked on a couple of years ago, I guess, or finished a couple of years ago. Um, so we've been terrible and not written it up, but I'm going to tell you the story, and then maybe there'll be some impetus to write it out. So here we go. So let's start with a little introduction. So this is a story about enriched categories. So if you've got an ordinary category, um, let's say C, so the arrows from X to Y form a set, C, X, Y. Now, in a V enriched category, C, um, arrows from X to Y are an object of V. So let's say an object CXY in V, where V is a nice monoidal category. Okay? All right. Um, well, I guess it really is a monoidal category. Uh, but you could say what nice means in more detail, but I'm not going to. And so we have many examples of this. So we could take VT set, in which case we just get back ordinary categories. But I could take the pose set, in which case I get categories with an order relation on the morphisms from X to Y that's compatible with composition. And that's a special case of taking our base for enrichment to be cat, in which case we get what are usually known as two categories. But then we can do other sorts of examples. So we could look at metric spaces. So if you're doing some kind of computer science stuff, then you might look at complete metric spaces as you might say that the arrows from A to B form a complete metric space, and that will allow you to form fixed points and things like that. And similarly, you might do CPOs with bottom. And I mean, you can carry on in this vein. Okay, now an important thing to note is that enriched categories are not categories. So categories are enriched categories, but the converse is not true because enriched categories don't have any morphisms. However, if I've got a V category, C, it does have an underlying category, which you normally write as C naught, and that has the same objects and maps in C naught from X to Y. What's that? Well, that just all the I-valued points of this Hom object Cxy in V. Okay, so I is the monoidal unit. Okay, so I here is the monoidal unit. So unit for the tensor product. Okay, all right. And so in that way, it makes sense to talk about having an enrichment of a category to a V category, right? So it makes sense to talk of enriching an ordinary category, let's say E, to a V category. So i.e., we find a V cat C such that C naught is isomorphic to E. Okay, so you might think I'm making a bit of a meal of this, but somehow this is the whole point. So normally you start with an enriched category and you might turn it back into an ordinary category. But in mathematical practice, often we start with an ordinary category and then we try and enrich it in some way to ascertain extra structure that it might bear and that we might be able to describe profitably in the language of enriched category theory. Okay, so let's look at some examples. So for example, if I look at complex vector spaces, well, that can be enriched over all sorts of things. So it can be enriched over set. Any category can be enriched over set. That's kind of just the definition of being a category, or at least a locally small category. But in C vector spaces, I can add maps together, so I can get enrichment over commutative monoids. Okay, but not only can I add them together, I can also subtract them, so I really have an enrichment over abelian groups. But in fact, not only can I subtract them, but I can also take real valued scalar multiples, so I get an enrichment over real vector spaces. And I can also multiply it by the square root of -1, and so what I get are Homs which are complex vector spaces. Okay, so these are all different enrichments of the category of complex vector spaces. All right, so maybe we'll just look at some other examples. So suppose I look at a pre-sheaf category, C op set. So that can be enriched over, well, I can enrich it over set again. So I could also enrich it over C op set, right? So any pre-sheaf category is Cartesian closed, so I can enrich it over C op set with the product. Now, maybe I can also enrich over C op set with some other monoidal structure, but just for any pre-sheaf category, I can certainly do that. And you might say, well, is there anything else I can do? So yeah, there are a few other things you can do. So I'm just going to list one of them. So what I can actually do is I can enrich my pre-sheaf category over the pro-functors, the C op times C set under this. So what's this? This ring is pro-functor composition. Okay. All right. And so maybe this is a bit less familiar. So what happens here? So for this last example, what do I have to do? Well, I have to tell you the Hom between two pre-sheaves, and that's going to be something from C op times C to set. Okay, so X and Y here are in C op set. So what does this Hom functor do? Well, it's going to take D, comma C, and it's going to send it to the set of maps from XD to YC. Okay. All right, so this is the Hom object. It's a pre-sheaf on this functor category. And so I have to tell you its value at every object. And so I get this. Okay, so you can see that somehow this is a lot more general than a normal pre-sheaf map. Okay. However, if I take this Hom object and I Hom into it from the unit of this monoidal structure, which is the identity pro-functor on C, what am I going to get? Basically, I just get a bunch of elements from xc to yc for each c, satisfying some dinaturality condition. And that dinaturality condition actually is just a naturality condition. It just says that I have a natural transformation from x to y. So you can see this really is an enrichment of the functor category. Okay, so maybe I'll just list a couple more, which are a bit more exotic. So let's see. So suppose I look at R algebras. Okay, so algebras over the reals. So that's enriched over R coalgebras. Okay, so in the sense of linear algebra. And so in this case, the point is that the HOMs are Sweedler's measuring coalgebras. Okay, and so what you can see here is that these measuring coalgebras, they encode not just the algebra homomorphisms from, say, C to D, they also encode things like derivations between algebra homomorphisms. Okay, so the algebra homomorphisms are just the group-like elements in this coalgebra. And then the, whatever you would call them, the primitive elements give you these derivations. Okay. All right, and just one more example that's even more exotic, but in the same vein. So if I look at monads on set, maybe accessible, then that's enriched over comonads on set, accessible. Okay, and so this is part of a Sweedler theory for monads due to Rivas, McDermott, and Ustalo. Okay. All right, good. So, okay, so we have all these different notions of enrichment. And so you might ask, well, okay, this dizzying array of things you can do, is there some kind of best way of enriching a given category? So question, is there a most general enrichment of a given category C? And the answer I'd like to propose is yes. No. In order to make that answer precise, I have to tell you what the theorem is. So the theorem has some restrictions. But here it is. So let C be a locally presentable category. Okay, so what does this mean? It means nice and algebraic. I'll give you the real definition shortly. So then the statement is that the two categories of locally presentable enrichments of C has a bi-initial object. Okay, and so that is, if you like, your best possible enrichment. Okay. So to sort of clarify, maybe this two category, which I haven't told you what it is yet, has a bi-terminal object, which is just given by enriching your category over set. Okay. So in a sense, that contains the least information about, you're adding the least information to your underlying category, which is none. And so this bi-initial object, by analogy, you can presumably add the most possible information that you could hope to capture about your category. Okay. Okay, good. So here's the theorem. I mean, I just stated the theorem, but I'm now going to explain the theorem and maybe even prove it. I mean, I'm not going to really prove it, but I'll write down enough stuff to make it look convincing. Okay, so as promised, what's a locally presentable category? So category C is locally presentable if C is equivalent to the category of kappa small limit preserving functors from T to set kappa small limit preserving functors from T to set for some small t with kappa small limits. Okay, so kappa is here a regular cardinal. The simplest case is that kappa is just omega or Aleph zero, in which case we're just looking at finite limits. And so we're looking at the category of models of a finite limit theory. Okay, so in particular, that includes the category of models of any finite tree algebraic theory, so things like groups, rings, k-vector spaces, and so on. But the category of models of a finite limit theory can also include things like posets, categories, uh, sheaves on a compact Hausdorff space, this kind of thing. Okay. And then if you go from finite, kappa being Aleph zero, to some bigger regular cardinal, then that allows for the same kind of stuff, but with possibly infinitary operations. So you might think, for example, of omega complete CPOs or something like that, which have countable operations. Okay, so there we go. So that's the sort of category that we're looking at. Okay, and there's a two category, which I'm going to call locally presentable tensor with, so objects are locally presentable monoidal closed categories. So I said monoidal closed, but really the point is that the tensor product preserves colimits in each variable. Okay. And the fact of it preserving colimits in each variable is the same as it being closed because we're locally presentable. So locally presentable means that things like adjoint functor theorems work just as well as they do for posets. Okay. And so what are the maps? So maps from like V tensor to W tensor. These are going to be lax monoidal right adjoints. Okay, so what do I mean by a lax monoidal right adjoint? You might think I mean a right adjoint that's lax monoidal, but that's not what I mean. I.e., right adjoint in mon cat lax. Okay, all right. So you might think I'm talking rather cryptically here, and that all these things are the same. So why is this not the same? I.e., has a left adjoint. Okay, but it has to be a left adjoint in mon cat lax. And so what that amounts to is that this left adjoint should actually be strong monoidal and not just oplex. Okay, so if you like, so this is Kelly's doctrinal adjunction. If you don't know what I'm talking about, you can just think that what I mean really here are lax monoidal right adjoints whose left adjoints are strong monoidal. Okay. Okay, good. So that's this two category. And so what we're going to do is we're going to sort of use this two category to define the enrichments of a given ordinary category E. Okay. So let's fix an ordinary category E. except ordinary. And then it's going to be a locally presentable category. So we're going to define what I'm going to call NE of V for V in moncat tensor to be the category so it's going to be the category of all enrichments of E in V. So objects are locally presentable V categories C together with an identity on objects isomorphism between the underlying ordinary category of C and E. Okay, does that make sense? So you have I've got an ordinary category E, and these are basically the enrichments of E to a V category. Okay? So I'm going to make a category of such enrichments. So a map from C to C primed identity on objects V functors which commute with the isomorphisms to C naught. Sorry, to E. Okay? All right, so that's the category of enrichments of E in V. I could even write that. So category of enrichments of E in V. Okay? So now we get a two-functor, which you might call enrichments of E in something. And so this is a two-functor that goes from moncat tensor into, Loc-Pres tensor into cat. So I just tell you what happens on morphisms, so which on one cells. So if I got F from V to W, so this is a monoidal right adjoint. So this induces E of F, which goes from the category of enrichments of E in V into the category of enrichments of E in W. And what does it do? Well, an enrichment C of E over here is sent to what's commonly known as F lower shriek of C. Let's say F lower star. Why not? F lower star of C, where what? F lower star of C is a W category with the same objects as C and the Hom F lower star C from wherever to wherever, X to Y.
Richard, we have a question.
Is just I take F and I apply it to the Hom from X to Y. Okay. All right, and the fact that F is Lex monoidal
Richard, can we ask a question?
allows you to pass the composition maps of your enriched category through this. Okay?
It's okay if he doesn't.
Right, so we've got this two functor. I mean, I've sort of sketched some of the details. I'm sure you could fill the rest in yourself. It's not too bad. And so now you could restate the theorem. The theorem I told you before says that this thing, enre is, I guess, by representable. Okay, so it's a functor into cat. So you can ask if it's a representable functor. And that tells you, if it is so, that there's some universal enrichment of which every other enrichment from which every other enrichment can be obtained by kind of restricting along a unique map F from the universal thing. Okay? And that all sounds very good because that tells us that every other enrichment is really just a pale shadow of this universal one. Okay, so why don't I try and prove this? Let's see what happens if I do that. Okay, let's see. So, big reveal, I'm going to tell you what the special enrichment is. So I'm going to write curly U of E be the category of all co-continuous endofunctors of E seen as monoidal under composition. Okay? So that's certainly a monoidal category. I think we can all agree on that. You'll notice it's not symmetric, but I very carefully didn't suggest that anything was symmetric at any point. Perhaps you see now why. But the other thing about it is that this is monoidal closed and locally presentable. Maybe I should swap those around. So first and foremost, it's locally presentable. And because of that, it's monoidal closed. I guess it's not symmetric, so really I should say monoidal biclosed or whatever. Okay. So that's a different bi from the bi 2 lines above. This just means closed on both sides. The one above means bicategorically. Okay, so why is this locally presentable? I mean, it's basically one of these. It's basically one of these limit theorem arguments, these accessible category kind of arguments. So it's in Greg Bird's PhD thesis, but it's not very hard to prove directly using this the limit theorem for accessible categories. So in particular, the fact that it's locally presentable, like it's one of these adjoint functor theorem kind of businesses, which means that you don't really have any good sense of how it's locally presentable in general. Okay. All right. So knowing that it's locally presentable, why is it then monoidal closed? Well, because its monoidal structure preserves colimits in each variable, right? Just visibly because you're looking at co-continuous functors. Okay. And so if I've got a co-continuous functor on a locally presentable category, then it will have a right adjoint. So that gives you your closure. Okay, good. So we're at least in the right ballpark. We've got a category of the appropriate form. So we have to just show, I mean, not just, the notable omission now is we don't yet know that E is enriched in this thing, okay? And maybe it's unclear why on earth we think that it might be, but all will be revealed. So what are we going to do? So we're going to apply a very basic result about enriched categories. And that's that you can construct enrichments from actions. Okay? So let's say in a monoidal action. So I've got a monoidal category. Then I can look at actions of that monoidal category on another category. And we have such an instance here. So let's call this action star. And what's it an action of? Well, I take UE, which is just the co-continuous endofunctors of E. And that acts on E just by application. So I've got a co-continuous endofunctor F. I've got an object X. What else could I do? I apply F to X. Okay? And moreover, this action, it's a bifunctor. And as a bifunctor, so this functor preserves colimits in each variable. Okay? Now again, we're locally presentable. So if I've got a functor that preserves colimits, then it's going to have a right adjoint. So by adjoint functor theorem, So if I fix an object E in E, then I get a functor blank star E going from U of E into E has a right adjoint, which is going to be, so I'm going to call it, I'm going to call it E underline E blank. Okay, so this goes from E into U of E. Okay. All right, and so for every E and E primed in E, we have E underline E primed in U of E, and these are the HOMs of an enrichment. Okay, so this is a super general fact. If I have a monoidal action and I have these right adjoints, then this gives me an enrichment. Okay, great. Okay, so we've got this. So now we just have to show that this thing. So we claim that this this E underline, which is this UE enriched category, which is an enrichment of E, is a bi-representing object, bi-representing element of this functor of enrichments. Okay, so again, let's try and, I won't prove it, but let's try and say some words about why this might be true. So let's see. So let's take C, and C is going to be a locally presentable V enrichment of E. Okay, so there's just some other enrichment of E. So goal, we want a Lax monoidal right adjoint going from UE into V, so let's call that F, such that F lower star of this universal enrichment gives me C. Okay, does that make sense? So C is just some enrichment. E underline is my nomenclature for the universal enrichment. And I just need to show that C arises from this universal enrichment via some Lax monoidal right adjoint F. I mean, not some, an essentially unique one, but for the purposes of this talk, I'm not going to do that. Okay, so how are we going to do this? Basically, we just run the argument that we had before in reverse. Okay? Well, for each E in E, what do we have? We have C E blank. Okay, so C is this enrichment. And so what that means is that I can take any object in E and produce from that this HOM object in V. And this thing here, and it preserves limits. And because C is a locally presentable enrichment, HOMing out of any object will be an accessible functor. And that's a sufficient condition, or a necessary and sufficient condition for it to have a left adjoint. Okay, so again, this is just some of the law of locally presentable categories. All right, and so, well, let's call this left adjoint blank star E. And blank star E goes from V into E. Okay? And these give an action. So I take these functors here, and from those I'm going to produce an action v times e into e, which, as it turns out, preserves colimits in each variable. Okay, so again, that's probably not obvious that it does that. And again, I mean, okay, so there's something sort of tied up in this thing here. I haven't really told you what a locally presentable V enrichment is. So what it really means is that this thing here is a V category, which is co-complete as a V category, and whose underlying ordinary category is locally presentable. Okay? And from those assumptions, it follows that this thing is not just an action, but one that preserves colimits in each variable. Okay. So why am I making a meal of that? Well, because that's equivalent to you take its transpose, so I can give something from V into co-continuous E, which preserves colimits. And this, remember, is just U of E. Okay. And moreover, it's strong monoidal. Okay. So that's the fact that, so this thing is a monoidal action. The monoidal actions like this correspond to strong monoidal functors like this, just like actions of a monoid on a set correspond to monoid homomorphisms into the endomorphism monoid. So, okay, so we have this, it preserves colimits and it's strong monoidal, and therefore, just because it preserves colimits, it has a right adjoint F, which goes from UE into E, and that's a lax monoidal right adjoint. Okay, so at this point, we're supposed to then, so this is the F I told you about before, right? Up here I said, we're going to find this F. So what do you know? We found this F, and now I'm not going to check that when I reindex my universal thing along this F, I get back the C that I started with, but it's true. Okay, and so because I just told you it's true, I now have a complete proof. Great. Okay, so there we go. So that's the idea. And really it's just sort of messing around. So it might look like I'm doing something, but I'm not really. I mean, really what's being done is this correspondence is really just this correspondence between actions and enrichments when you have these adjoints here. Okay. Okay. So that's the result. But it would be quite uninteresting were there not some examples. And I mean, there are heaps of examples because there's heaps of locally presentable categories. However, there are rather fewer tractable examples in the sense that you can compute explicitly what UE is and then go on and compute explicitly what the Hom objects of the enrichment are. Okay, so those are both non-trivial problems, and you may be able to solve the first, but not the second, although you can't possibly solve the second if you can't solve the first, I presume. That's not necessarily true, I don't think, but in any case, I have a bunch of examples where at least one of the problems is solvable. In fact, the first one, and in fact, both of them. So let me show you some examples, basically. So here we go. So what's the least interesting example you could come up with? Well, set. Okay. So what happens in this case? U of set. So it's some monoidal category. The monoidal category are co-continuous endofunctors of set. Okay, now set is the free co-continuous, free co-complete category on an object, where the object is just the one element set. And so giving such a co-continuous endofunctor is just the same as giving a set. Okay? And so U set as a category is equivalent to set. Okay, and the co-continuous endofunctor corresponding to a set A is the endofunctor that just multiplies by A. Okay? And so what happens when you compose two such functors? If you compose multiplication by A with multiplication by B, then you get multiplication with A times B. Okay? And so when you transport back, what that tells you is that the monoidal structure you get is product. Okay? So somehow the Cartesian product of sets, you don't even have to know that it exists, right? It's just there for the taking when you look at the co-continuous endofunctors. Okay. So, and in this case, set underline, which means the universal enrichment of set is just set, right? Because it's just the set enrichment of set, which is just set. Okay. Okay, let's do some more. So, complex vector spaces. So what's U of complex vector spaces? Well, as it turns out, it's complex vector spaces. So the co-continuous endofunctors of complex vector spaces are all given, are all of the form V tensor blank for some complex vector space V. And in fact, those categories are equivalent. And just by the same argument as before, it follows that the tensor product is the tensor product. Okay? So in fact, the tensor product of complex vector spaces is again just sort of there for the taking. And if I look at the canonical enrichment of complex vector spaces over complex vector spaces, and this is the canonical self-enrichment. Okay, and the usual one, the one you expect. Okay, and so that happens for abelian groups and real vector spaces, sorry, R modules, all that sort of stuff. Yeah. Okay, so let's try one that's less non-trivial. How about groups? Okay, so you can say, well, what is U of group? Well, U of group is co-continuous endofunctors of the categories of groups. Okay, and what is that? So the opposite of the category of groups is the limit theory of groups, in the sense that a limit preserving functor from group op into E is the same as an internal group in E. Okay? So a co-continuous functor from group to group is the same as a limit preserving functor from group op to group op. And so it's the same as a group object in group op. So it's the same as the category of co-groups in group. Okay? And so this is sort of in general true. If I take some algebraic-y thing here, then the co-continuous endofunctors are just given by co-algebraic thing in my algebraic thing. Okay? So what does that mean? Well, it means I've got a group G. It's got a map to the one element group, which is not very hard. And this is the free product of groups. Free product of groups. And I guess there's an inverse thing here as well. Okay, so that's a co-group in groups. I mean, maybe you have to put a little circle on these or something. I don't know. That's what a co-group in groups is. And what is that? Well, amazingly, it turns out to just be the category of sets. So what does that mean? Well, if I take any free group, that is a co-group in groups, because every set is a co-group in sets. Okay, just via the what do you call it? The codiagonal and the unique map. Okay, that make sense? I don't know if that made sense. But it's certainly true that every free group is a cogroup. And the free group structures correspond to bases for your free group. And from that, it follows that the category of co-grouped and group is really just set. Okay? And sort of amazingly, this result is due to Dan Kahn in 1958. Okay? All right. And so actually, I mean, he doesn't say this, but it's then just with the Cartesian product. So in this case, there aren't any better enrichments of groups than just the ordinary category of groups. Okay? Okay, let's do one more that's less hard. So we're going to do C set. Okay, so in this case, the easy part is this. So what's U of C set? Well, it's co-continuous endofunctors of C set. C set is the free co-complete category on C. And so that's equivalent to functors from C to C set, which I can just think of as C times C set. Okay? And then the composition operation is just profunctor composition. Okay, so remember, this was an enrichment. Sorry, this was a base for enrichment that we discussed earlier with respect to pre-sheaves. And then the enrichment C set with this enrichment over the profunctors is as above. Okay, so remember, I wrote down a formula before. So maybe I'll just explain a little bit. I'm only going to do it for this example, but maybe I should explain a little bit about how you actually compute these enrichments. So, okay, it's pretty obvious that we know what U is in this case, U of E. So how to compute the enrichment. And basically, you just move things around under these adjunctions and use the Unay dilemma. Okay? So, right, so basically the idea is that in the end, what you'd like is that this category U of E, you know some nice set of generators for it or something like that. So in this case, I do know a nice set of generators for this, namely the representables. So what do? I say if I'm given X and Y in C set, and I want to know what EXY is, the set of maps from the representable at D, C into this Hom object in C times C set. Okay, now, really don't want to be there. We want to be in co-continuous C set. And so we need to know what this corresponding functor here is. So let's call it just L into EXY. Okay, so I guess the point, so I'm being a bit pernickety here, right? But this thing here is something in here, and it corresponds to a co-continuous functor like this, right? So I view this as a functor from C into C set. And I can't extend it to get something like this. Right, and so then what do I do next? Well, then I use this adjointness, right? So the adjointness tells me that these are the same as maps from Lx to Y in C set. Okay, so that's literally the definition of this object here. It's just it's defined by this adjointness. Okay, so this doesn't look much better. I mean, I could compute this, but it'd be a bit of a pain. What's actually easier still is to take the right adjoint of that functor. So I mean, this thing Lx is like a left-Kahn extension, right, of a functor from C into C set. Whereas this R thing here is just the nerve functor associated to that, and that's much easier to write down. And so we might as well just do that. And so now we just work out what R of y is. So calculate the R of y. What does that come out to be? Let's look at my cheat sheet. R of y is a functor. It's a presheaf on C. And so what's it given by? Well, it's given by C d blank. So remember we fixed an object little d and little c, yc. And therefore, I can say now that maps from x to ry are the same as what? Well, I give maps from x into c d x y c, natural in x. And then I do another Uneda thing. And so that's just a map from xd into yc. Okay, which if you think back, so that tells me that in this enrichment, I look at the maps from x to y, evaluate at dc, I just get x d y c. Okay, phew. Right, so that was a little calculation. As I say, I don't want to do any more of those calculations, partly because I haven't got time, and partly because that illustrates all of the basic phenomena that you're going to see. So basically, you just do the same thing every time. You take this E that you're trying to find, you hom into it from some generator, and then you take a transpose. It's probably easiest to transpose that back over here because computing this thing's generally harder than computing this thing. And this thing will always have a right adjoint. And then just work out what this amounts to, and Bob's your uncle. Okay, good. So let me show you some the fun examples. I haven't got very long, but I'll show you the fun examples, or some of the fun examples. So more fun examples. Okay, so here's one. So I'm going to let E be the category of I pointed sets. So I is any set. Okay, so if there's just one I, if I is a singleton, then it's just pointed sets. But this is a set with a whole bunch of points. Okay. So in this case, U of E, what is something in U of E? Well, it's an I pointed set together with I co-points. So has objects. So it's going to be an I pointed set, which I'm going to call F goes from I to X. And then there'll be a family of co-points. So they look like this, and they go into the they go into the initial object in this co-slice category, which is just the identity map. So, and this is for each I and I. Okay, so that's what an object is, or equivalently, I give a map from I into X, and then I give a map from X into functions from I to I, such that E composed with F is just the constant function from I into I comma I. So the constant function takes little I and sends it to the function that's constant at I. Okay, so you might call that pi1 transpose. Okay. All right. Okay, and so this was actually discussed in some detail in a paper by Zibladze in 95, which is called Some Strange Monoidal Categories. Okay, so this is, I agree, it's a bit of a strange monoidal category. So it's got a monoidal structure, which is so strange, I'm not going to describe it. But I'm going to tell you what the enrichment is. So the enrichment of E in U of E has what? Has the following. So I've got to take two I pointed sets, X and Y, And then what have I got to give you? Well, I'm going to give you a set of maps with a map from I and a map into functions from I to I. Okay. So what's the set of maps here? So what I'm going to do, I've got I going down to X and I've got I going down to Y. Okay, now a normal map in the co-slice category would involve like an H along the bottom here, and then it would commute with the triangle at the top. Okay, so I'd put the identity at the top. But in this enrichment, I'm also allowed to put a G here. Okay, so if you think about it, what that's saying is that I've got these I points, but when I map from X to Y, I'm allowed to rearrange the points in some way. I mean, I don't, not even necessarily bijectively, but I have to send the chosen points to some other chosen points, but not necessarily the same chosen point, if you see what I mean. Okay. All right. And so then this bit here just projects onto the domain part. So it just takes the G. And then this map here, F, so what does it do? It takes I here, and it's going to take it to the following thing. So I can go from X to Y. It'll just pick out the constant maps. Okay. So this is just going to be constant at little I. And this is just going to be constant at the ith constant of Y. So constant at GI. Okay. So again, if you think that I was a singleton, then this thing here picks out what you would normally call the zero map. Okay. Because here we'd just be looking at pointed sets. And then this thing here would pick out the zero map. This thing here would have no meaning at all. Okay. It would just, this is just singleton. But suppose I have a whole bunch of points, then I have a whole bunch of like zero maps, which correspond to each of the given points. But then these special maps here allow me to not just map the points across directly, but to rearrange them in some way. Okay. I've just got a couple of minutes left, so I'm just going to show you very briefly one final example, which I can do briefly because it doesn't take very long. So E is sheaves on X, where X is a stone space. Okay, so it's the space associated to a Boolean algebra. So in this case, you can kind of work through what this means. So U of E is the category of co-sheaves in sheaves. And it turns out that that can be described as the category of spans of the following form. So I take X here, I've got R, and I've got X. And it's going to be a span of topological spaces where this left-hand map is a local homeomorphism. Okay? So in this case, what's this enrichment? So E underline from a given sheaf on X, which I'll represent as a local homeomorphism. So it's going to be something like this. So it's the span of this form star, where R down to X, this local homomorphism, has local sections over U given by the following kinds of spans. So what do? I take A down to X. I'm going to take this open subset U here, take a pullback like this, and then I just give any span, any map at all down to Bx here. Okay. So again, you can see that for a normal map of sheaves, first of all, it would be globally defined everywhere on X, on A, sorry. These are only partially defined. But not only that, I'm allowed to map non-trivially on the base space. Okay. And so in that sense, you're capturing a lot more than you would with just an ordinary, just the ordinary HOM. But this is sort of the maximum stuff that you can capture. Okay, good. So that's probably a good place to stop. There are other interesting examples you can think of, so George Bergman has done a lot of work on this sort of stuff, and using his work, you can do this for monoids, and that's quite interesting. And you can even try and do it for magmas and things like this. And then it gets really interesting because it's somehow related to some topology just shows up out of nowhere. Okay, great. So thank you for your attention. And I think this is the right time to stop. I hope it's the right time to stop. So thank you.
All right, well, everyone can use their little clap emojis to send thanks to Richard. If anyone has, maybe we can take a couple questions, quick questions. So if you want to use your hand raise emoji, want to ask a question. Let's start with James. Do you want to unmute yourself? Oh, yes,
Yeah,
no, maybe.
So I was wondering about the connection between the category of things to enrich in and the opposite of the category of pseudo-monoids for the or two categories of pseudo-monoids for the tensor product of locally presentable categories. Are those the same thing, or is there some difference?
They're the same thing, yeah. So there's the tensor product on locally presentable categories that classifies functors that are co-continuous in each variable. So that's a monoidal closed bicategory. And yeah, if you just look at the pseudo monoids in there, so really you'd sort of, it would be the opposite of this enriching category. So that category you'd have the strong monoidal left adjoints as your morphisms. So I've chosen to take the lax monoidal right adjoints just because those are really the forgetful functors. So somehow the corresponding left adjoints are like, if I change base along those, that's like a free functor or something like that. But the lax monoidal right adjoints are like the forgetful functors. But yes, up to that caveat, that would be the same two category.
Yes, I guess I like them in the opposite direction because it makes the thing you created more like more like a classifying object.
That's right. So that would be the geometric direction if you took the left adjoint functors, I guess. Is that right? No. No, this direction is the geometric direction. Is that right? No, the left adjoints are the geometric. The left adjoint's the logical direction. This is the geometric direction. Yeah, good. Okay.
Okay.
Maybe we can move to the next question. Kaya?
I was wondering if you've thought about doing this sort of thing for families of categories all at once. So that would I'm imagining something like you take all of the semi-additive categories and you say that their common denominator of enrichment is commutative monoids or something like that.
That's interesting. I haven't thought about that, but that's a good idea. It would be like taking a kind of like a co-density thing or something like that somehow. That's a great idea. I haven't thought about doing that, but yeah, I reckon that would be quite interesting. So I mean, I do know something about that, but it's a different thing. But it's related, I suppose. So if you take set and you universally make finite coproducts absolute, then you get commutative monoids. So I think that's related, but I mean, maybe what you suggested would give another way of formulating that. That's a very nice idea. Thank you.
And maybe the last question from Jack.
Hi, sorry. So I just have a quick question. So the universal enrichment of like the complex vector space itself, but for abelian groups is the set. So do you have like an idea? So for what rings, like the universal enrichment of R modules, like is R module itself? Like
Right. That's a great question. I think it's true for all rings. Is that true? I don't know if that's true or not. It might not be true, but I have a vague feeling it might be true for all rings. But it's certainly not true for all. So all these things are commutative monads on set. So you have this canonical tensor product on the algebras. But I believe that there are commutative monads on set for which there are more co-continuous endofunctors than there are just objects. So I think
But for abelian groups, it's already set, right? That's Z module.
for abelian groups, I think the universal enrichment is abelian groups, isn't it? So I think
Oh,
so
I
you
thought.
can.
Oh, right. That's for groups. Sorry. Yeah,
Oh yeah, for groups, yeah.
Yeah.
For non-abelian groups, it's just set. That's right. But for commutative theories, it will always at least be the the category itself, but there might be more stuff, I think. So I think I haven't really worked it out, but one example I think is plausibly has this property is you can look at the finite distribution monad on set. So the algebras for that are these abstract convex spaces, but I don't have a proof that it's not, but I believe that there are more co-continuous endofunctors than just tensoring with an object in that setting.
Thank you.
All right. Well, thank you very much again, Richard, for the first talk in the PCT. And I also want to thank my co-organizers, Zainab and Soichiro, who definitely did a lot more heavy lifting than I did to organize this. So I hope you'll join us for the second iteration next time, which will be on January 16th. And until then, I wish everyone happy holidays, Merry Christmas, Happy New Year, and a good break, I hope. So thanks again for joining us, and see you in a month.